Hello and welcome back to the Science for Concrete Materials class. This is lecture number 18 of the class and we are still on the SCMs topic. This will be the third and final lecture on the SCMs topic. In the previous lecture we covered the most commonly used SCMs, pozzolans and the slag. Today we will discuss how these SCMs influence the concrete properties. For the fresh concrete properties, we will talk about how the SCMs influence the water demand, workability, bleeding, heat of hydration, air entrainment, and setting time. For the hardened concrete properties, we will talk about the mechanical properties, strength, for example, and the durability, which is basically how the microstructure is influenced and how will that help the durability of the concrete. Okay, as if you remember, back in some of the lectures we mentioned, our ultimate goal is to improve the performance of the concrete by making it more durable and more sustainable. And the use of SCMs does both. Okay, so the effects of the SCMs on water demand. How does that happen? The fly ash decreases water demand, basically due to the ball-bearing effect of the spherical particles. So that basically for every 10% replacement of fly ash, there is a 2 to 3% reduction in water demand. Reduction in water means better durability. The silica fume may increase or decrease the water demand depending on the replacement level. For 2% replacement, water demand is reduced. For more than 5% replacement, water demand is increased. You remember I said due to the very fine and sticky nature of the silica fume, handling becomes difficult. For the slag reduces water demand. So if you compare these last three products we talked about, fly ash, slag, and silica fume, the most reduction in water demand comes from the fly ash, followed by the slag, and then the silica fume. Okay, the effect in workability, which also a big deal. Silica fume containing concretes tend, as we said before, to be sticky and more difficult to finish, so leading to decreased workability. In that case, of course, we will need to add, high range water reducers in order to improve workability, rather than adding water. Okay, we have the blessing of using these admixtures, which we will talk about in the next module of the class. Slag and fly ash generally improve workability. Okay, as far as the effect on water bleeding, fly ash reduces bleeding. Slag may increase or decrease bleeding, depends upon the fineness of the slag particles. Fine particles decrease bleeding, and the coarse particles, have less of an effect. In the case of silica fume, it decreases bleeding and may eliminate it altogether. By this, making finishing difficult. So you have to remember, when adding silica fume, other measures have to be taken in order to make sure we have good finishability of our concrete. Okay, on the heat of hydrations, just in general, most SCMs reduce the overall heat of hydration and rate of heat liberation. Basically, this is good for mass concrete or large sections, for concrete in hot weather. The use or the introduction of the use of the SCMs eliminated really the need for the type 4 cement, the low heat of hydration cement, because this is basically a cheaper, more convenient way of reducing the heat of hydration. So let me just say the following. As we said, mineral admixtures reduce the overall heat of hydration, and in particular the rate of heat liberation, which controls the temperature rise in hardening concrete. The use, as I mentioned, the use of a mineral admixture is equivalent to raising the C2S content of a cement, and effectively turns type 1 cement into type 2 or type 4 cement by doing that. As I said, the use of pozzolans in mass concrete, has eliminated the production of type 4 cement in the US, except of course for oil well applications. If you remember, we talked about the special cements and the types of cement lectures about the oil well cements. Is still low heat of hydration still an issue, although these cements still produced in Canada. Anyway, although the heat of hydration of the pozzolanic reaction is generally considered to be low, as we mentioned, it may actually be higher when normalized on weight basis. You remember, we replace a lot of the cement by a mineral admixture. We end up with lower heat overall and lower heat generation. But on a normalized basis, it might be higher. But since the reaction is slow, the heat is released slowly, and the temperature rise in mass concrete is invariably reduced, as you can see, for example, in this figure right here. This is a Portland cement alone without replacement. This is Portland cement with fly ash. This one here with a slag. As you can see, of course, under moist curing condition, with time and the temperature rise. As you can see, it's reduced, the overall temperature rise. And again, the reaction is slow, so the heat rise is much lower. Okay, as the effect on air entrainments, we said concrete containing mineral admixtures still must be air entrained for frost resistance. The frost resistance or the air entrainment will be discussed later. Unless the water cementitious ratio or water to cementitious material ratio is below 0.24, then there is a different set of requirements that probably will be beyond the scope of this class, which is the high performance concrete. But in that case, there may not be a need. The addition of a mineral admixture will often change the amount of air entraining agent required to achieve a specific or a specified air content. So that is usually due to the residual carbon within these admixtures, strongly inhibits the air entrainment, especially when fly ash or rice husk ash are used. But even when carbon-free pozzolans still can affect air entrainment. So the appropriate adjustments must be made when proportion in such concretes. Again, we said trial mixes are key in order to be able to understand and really verify the effect of any addition to their concrete mix. Okay, for setting time, generally slag and fly ash, they lengthen the setting time by about 50 to 60 minutes for the initial set, and somewhere between 30 to 120 minutes for final set. Class F fly ash lengthens setting time even more than Class C. Of course, that, you know, being dependent upon the chemical composition. But said class C contains lime. That's why probably. The silica fume reduces setting time, of course, due to its high reactivity. And we mentioned that several times before. This is a good table here, actually, which summarizes the effect of these SCMs on the fresh concrete property. This is obtained from PCA, Portland Cement Association, and it gives you here really an indication of what every SCM will do to any of these properties. Okay, so let's move on and see what's the effect and how these mineral admixtures or supplementary cementitious materials, you know, impact the microstructure. Mineral admixtures modify the microstructure of the hydrated matrix quite significantly. So the increased fraction of the calcium, we said, you know, we have increased calcium silicate hydrate due to that pozzolanic reaction. The increased fraction of calcium silicate hydrate leads to a more homogeneous microstructure, particularly when high reactive, finely divided pozzolans are used. Okay. The residual calcium hydroxide crystals are usually smaller and can have altered morphology. So the principal effect on the microstructure is the change in pore structure. Okay, so admixtures, you know, admixture reactions will reduce the overall porosity because, you know, the specific gravity of the calcium silicate hydrate is lower than that of the calcium hydroxide. And also they will reduce the pore size, not just the overall porosity, but the pore size as well. However, you know, a reduction of the porosity requires extensive pozzolanic reaction produced by prolonged moist curing. Again, we go back to the practices in the field. Moist curing is key in this case. Okay. Also, reductions in the overall water cement ratio will produce larger reductions in porosity. If you remember, you know, when we use some of these mineral admixtures, we reduce the water demand because we get better workability. So the reduction in the water cementitious ratio, the water to cementitious materials ratio, also plays a role in reducing the porosity. The particle packing characteristics of silica fume, for example, are particularly effective in reducing the pore size. And for this reason, silica fume is used extensively in bridge deck overlays to reduce the rate of chloride penetration to the reinforcing steel. So that's one great advantage of using silica fume. The effect of the mineral admixtures on pore size distributions are summarized on this figure, as you can see here, where, as you said, you know, this is a familiar curve. If you remember, we talked about, you know, this is a comparison of the size distribution of a cement paste made with mineral admixtures, you know, using the mercury intrusion porosimetry. This is the accessible pore volume, and this is the effective pore diameter. And you can see the reduction here in the threshold, the pore diameter, the threshold pore diameter, and the effective pore diameter, somewhere around here, or the critical rather. So this is the control mix, and this is the fly ash replacement, lower. This is for the silica fume. Of course, it's even lowered more, and with the slag is lowered even more. The effect of the slag here may be due to the higher replacement, maybe, but nonetheless, this gives you an indication of how the use of these mineral admixtures or SCMs will refine the pore structure by reducing the overall porosity and reducing the pore size. Okay, on strength development, you know, concrete containing mineral admixtures will develop very good strength over time, exceeding those of similar concretes without admixtures. The extent to which the replacement of cement by mineral admixtures will lower the early strength depends on their reactivity, as we will see in the next slide. Reductions in the early strength, can be offset by lowering the water cement to cementitious materials ratio, with also the use of, at the same time, the use of the water reducing admixtures. At the early ages, some mineral admixtures essentially behave as an inert addition, so that the cement reacts with an effectively higher water cement ratio at the beginning. However, highly reactive pozzolans such as silica fume or calcined clay or rice husk ash will actually decrease setting time slightly and contribute to early strength, as we mentioned that before. The pozzolans, influence the cement hydration. These pozzolans, the one I just named, the three, they influence the cement hydration immediately and start to contribute to the strength within the first few days due to their high reactivity. This here figure shows the effect of adding the various or the different mineral admixtures to the strength. Let's, for example, talk about, this is the control mix with the solid line here. And you can see the Class C, Class F fly ashes and the slag right here, replacement, they all have lower early strength, as you can see, up to almost, 14 days. These are almost up to 28 days, the Class F fly ash. Then after that, of course, they all show higher strength. The silica fume and the silica fume right here and the rice husk ash, they both had higher early strength, as you can see, than the control mix, as we mentioned on the previous slide, due to their high reactivity. Okay, but overall, long-term strength is higher for all SCMs with all replacements. Okay, let me see, go back here. Okay, as for the effect on durability, mineral admixtures are used extensively for improving the durability of the concrete, which will result in better sulfate resistance, as I'm going to show on the next slide, control of the alkali-silica reaction, decreased chloride diffusion, and reduction of leaching and efflorescence. Because why? Because we removed the calcium hydroxide in the pozzolanic reaction. So improvements in durability results from the reduction in the calcium hydroxide, which is the most soluble of the hydration products. Also from the changes in the pore structure, as I've shown in the previous slide, and the reductions in the water to cementitious material ratio. All these three factors combined result in an improved durability or change in the pore structure. The natural pozzolans, as I mentioned, were first used in the U.S. to add resistance to sulfate attack in these structures in California, as if you remember in the introduction. So pozzolans, reduce the amount of ettringite that can form, for example, in several ways. Firstly, they reduce the permeability of the concrete and inhibit the ingress of soluble sulfates. That's one way. Secondly, they reduce the amount of calcium hydroxide. Remember, we said calcium hydroxide is taken from the system. By this, they will limit the formation of gypsum from the soluble sulfates, because soluble sulfates will react with calcium hydroxide to form gypsum, which will participate in the ettringite formation. Okay. The third way they help, their addition as an admixture reduces the effective C3A content of the cement because we reduced the cement content. We replaced it with SCM or one of these pozzolans or slag. So basically we reduce the C3A. So 3 ways the use of SCM can help, improve the resistance to the sulfate attack and the ettringite formation. You have to remember the reduction of the calcium hydroxide is an important aspect since it can leach out over time, thereby increasing both porosity and permeability. So again, the removal of calcium hydroxide from the system, helps manifold. Okay. Also, as we said, the sulfate ions, can enter the concrete more readily, and calcium hydroxide now becomes, a convenient source of calcium to concentrate and form gypsum, and eventually, as I said, I'm repeating what I said, to form ettringite. So the removal also helps that. I'm going to show on the next slide, as I said, the reduction in expansion due to sulfate attack when we use mineral admixtures. When we use type 5 cement with mineral admixtures, we can even provide greater resistance to sulfate. So that's something also you need to keep in mind. Also, mineral admixtures, as I said, reduce the expansion due to the alkali silica or alkali aggregate reactions, as that subject will be discussed later in durability. So the relative abilities of the different admixtures almost parallel their influence on sulfate expansion, which is primarily due to the reduction of the alkali content of the cementitious blend and the reduction in the pH of the pore solution, because we took calcium hydroxide out. Also, you have to remember the calcium silicate hydrate formed in the pozzolanic reaction can absorb alkali ions to a greater extent than that formed by the hydration of the calcium silicates alone. Okay, so the admixtures, have high alkali contents, may be less effective in this case. As we mentioned, it is also known that, not all pozzolans improve sulfate resistance to the same extent. Okay, since, those with high alumina content can form the calcium aluminate hydrate compounds I've shown equation number 3 before. These compounds, that will increase the potential for ettringite formation. Also, one more thing, the increased calcium oxide content in Class C fly ash will reduce the consumption of calcium hydroxide in the pozzolanic reaction. So the benefits we get from the fast removal of calcium hydroxide from the system will be less effective in the case of the Class C fly ash, for example. Okay, this figure here, as I mentioned in the previous slide, shows the potential linear expansion of the concrete versus exposure time in months here. And you see this is the control mix, and here is the replacement with slag, which is the best performing. This is with silica fume, this is with fly ash replacement. So evidently there's an improvement in that aspect where the linear expansion has been reduced. Also, as far as durability, the reduction in pore size results in general a decrease in transport properties, and the water permeability and the ionic diffusion. So which are, basically this is often the rate limiting properties in any chemical attack, permeability and the transport properties. Okay, so using the SCMs will do a lot in this case. A decrease in the chloride diffusion is the major reason for the reduction in chloride penetration, when mineral admixtures are used. As basically you can see here in this figure. This is chloride penetration into concrete mass percent in top 25 millimeter, which is here time of exposure in days. You can see this is the control mix. This is with control mix with higher water cement ratio. It's even worse. Look what happened when we add SCMs with his 25% fly ash replacement. Of course, definitely there is a decrease. Look what happens when we replace 40% with slag. Look what happened when we replace 10% with silica fume. You remember we said silica fume is used in the overlays, deck overlays, bridge deck overlays before, and just see the improvement from using none to 10% silica fume. Of course, this is with high replacement with slag, 70%. Of course, replacement with slag with this much is only probably recommended in few cases. Sometimes when you need early strength, you cannot use this much replacement of slag. But nonetheless, in certain applications where early strength maybe is not important, the benefit we get in terms of durability could be it could outweigh the other benefit. Okay, so basically, just you could see from the previous this presentation and so far how these SCM improve the concrete properties. Here is a summary similar to the one I showed for the fresh properties. This is the effect on hardened concrete properties, and you can see almost a benefit in every way we use these materials. Great materials to use. Waste products are being turned into magic products to help improve the concrete durability and concrete sustainability. Okay, so now we finished the talk about the SCMs. Let's talk about the remaining topic, which is the blended cements. As I mentioned, I'm going to mention this topic after we finish the SCMs discussion. Okay. Although most pozzolans and slags are used as mineral admixtures, a few cement companies, maybe some in the US and Canada, offer Portland pozzolan or Portland slag blended cements. In Canada, also a Portland silica fume blended cement is available. So again, you have to be careful sometimes when using certain cements. Some ready-mix suppliers may use blended cements and still refer to it as type 1. You have to verify the mill certificates and make sure what is being used. These cements, must conform. The blended cements must conform either to ASTM specification C595 or to the performance-based specifications ASTM 1157, if you remember. This table here summarizes the type of blended cements according to ASTM C595. There is a little difference in the performance in the way of the admixture added, only in the amount added. The use of blended cement, offers convenience and quality control and eliminates the need to handle an extra ingredient at the ready-mix concrete plant. The disadvantage of it is that the pozzolan or slag is added at a fixed level, which may not be optimum for a particular application. So my preference, my personal preference is to always use it as an addition at the concrete mix supplier rather than the use of the blended cements. And again, I'm not saying do not use them, but this is my preference. Okay. So while ASTM C595 provides compositional limits, it's still basically a performance specification. Like C150, it offers composition limits. And also use the same tests and same or similar limits on performance. Unlike, C1157 is purely a performance-based specification with no compositional limits imposed. As you remember, we talked about the 1157. At the end of the day, as I mentioned before, I look at cements all in general as performance-based cements, and the engineer, the designer, or the construction professional who is ordering and specifying the concrete must know all these details and must be able to specify which cement to be used when, where, and how. And that's how I look at it. Every cement is a performance-based cement in general sense. Okay? By this, really, we come to the end of lecture number 18. And this is basically the end of the SCM topic module. We finished the cement module, all of it. And next time we will start on the second module of the class, which is the chemical admixtures. Thank you for watching, and I hope I'll see you on the next set of lectures. And again, as I mentioned before, I appreciate and welcome any feedback, any comments, whether positive or what could be perceived negative comments. I welcome all comments, and the intention at the end of the day is to help to improve my performance in order to be able to help the audience in any way I can. Okay, thank you, and we'll see you next time.